So this is the lecture for the first PowerPoint for AP Physics C, Chapter 13 on fluids. So starts out pretty basic. They talk about density, just basic equation, density equals mass over volume. We talk about fluids. They're not compressible in lab situations, so generally the density is going to be the density. There talks about in the beginning of the chapter also standard temperature pressure, 0 degrees Celsius, 1 atmosphere. Should also be able to convert very fluently between atmospheres, kilopascals, millibars, millimeters of mercury. Those are all the same number, millimeters of mercury, millibars, torricellis. They're all 760 per 1 atmosphere. They're just different names for that same unit. So be able to use dimensional analysis to convert back and forth real easy between those. So when we talk about pressure in a fluid, just pressure in general in physics is always pressure equals force over area. So you know, the idea is that if you have a certain amount of force in newtons and it's spread over a wider area, of course there's less pressure. If you have a narrower area, like say somebody's walking over you with shoes, you're okay. But if they walk over you with high heels on, it's not so good because it's focusing on a narrower area of contact. The SI unit for pressure is Pascal. Even though we use the kilopascal more often, you know, the kilopascal is just more of a usable unit, which is 1 Newton per meter squared. And that makes sense because force is Newton, area is meter squared. Again, atmospheric pressure, be able to convert fluently 1 atmosphere, 1.321 kilopascals, 14.7 pounds per square inch. So, you know, we're going to have problems where they ask you to solve for the pressure at a certain depth, P sub D. To do that, it's kind of like somebody stacking weights on your stomach when you're laying down. Every weight counts. So look at what we have for the equation. P sub 0 would be what's the pressure at the top of the fluid, and then it's density times G times H. The rho, we use rho for density. G is 9.81 meters per second square. H is in meters, has to be in meters, and that's how deep the fluid is. So, you know, you could do this multiple times. Let's say we had 5 fluids all stacked up. Well, you could figure out what the weight is at the bottom of the first one, and then that will now become P0. And then you figure out the next one, and then once you figure out the beginning of the next layer, that's now P0. So you could figure out each layer in sequence. Practice problems 13.2 and 13.3. They had one pretty interesting one that gives you a chance to use some calculus on in the book. So that would be a good couple good ones to work through. They give you the solution. Make sure you can follow through on that. That's page 378, 379. Bulk modulus is just basically a complicated term for how much a fluid can be compressed. And yes, in lab conditions, generally we consider them to be non-compressible, but there's a very slight amount of compressibility, and this is what bulk modulus measures. The letter for bulk modulus is B, or a lot of books use K, so be ready for either one of those. It's basically the compressibility of a fluid. I know we said that they're not compressible, but you know, under lab conditions generally we talk about them not being compressible. There's a slight compressibility, and that's what this solves for. Bulk modulus, which is either K or B, is the bulk stress over the bulk strain, which is force over area on top, which that would be the bulk stress, over the change in volume over volume, which would be bulk strain. In other words, how much it strains or changes with the pressure that you have on top. And again, the force over area, basically delta P, delta pressure. So the more difficult the fluid is to compress, the smaller is the delta V over V. In other words, if it's 0, then you can't compress it at all. If it's a slight number, which usually is a very small number, then it is slightly compressible. So Pascal's principle, this is the law that talks about transmission of pressure through fluids. And this is how the old car lifts used to work. They would have a large cylinder, and you'd drive the car onto this ramp, and underneath it there's this large cylinder, and then somewhere else there's a compressor that's pressing fluid into a smaller cylinder, and it's forcing that fluid to go up underneath the vehicle, and it fills up this space underneath and raises the vehicle. So Pascal's principle states that the pressure exerted anywhere in a confined, incompressible fluid is transmitted equally in all directions throughout the fluid. So the problem here, that I guess the math problem that you're going to see, I've got some examples that you should work through that are from the physics book, that it's usually the car lift problem where they have a small cylinder and a large cylinder, and they're asking you to solve for the force that's required in one of the cylinders in order to make the whole thing work. Here's an example of this Pascal's principle type problem, and we've shuffled things around here. Basically F2 over A2 equals F1 over A1. And in other words, the force is proportional to the area. So we've swapped, or Anderson swapped the A2 up on top and kind of knocked that F1 over, but A2 and F1 are up on top, and we're solving for the F2. So, we could do just the opposite and solve for the F1. Sometimes they ask how much pressure do we have to put in the small cylinder, or force. Sometimes they say how much force is put into the large cylinder. So that's your basic problem. And again, it's easy to remember that F2 over A2 equals F1 over A1. So you start with that basic equation, and you can see some different varieties down here on the bottom of how you could shuffle this around. They could ask, if you move the small cylinder this far, how far does the big cylinder go? And the idea is that you're multiplying force, but you're having to give up. So you can see here's the distance we move the big cylinder, and we have to move the small cylinder that far. So the idea is just like a lever. You have to move a lever a long ways with a little force to move something with a great force a small distance. And that's the type of situation you have in this apparatus. So buoyancy and Archimedes' principle. The story is an old one. They talk about how Archimedes was trying to solve a problem for the king. He had been given a crown, or he bought a crown, and he was suspicious that the crown wasn't real gold. And he asked Archimedes to find out a way. Well, Archimedes went to a bath, which at that time was kind of like a local spa, but kind of a combination of other things too. And he was sitting in his bath, and it had been filled up all the way. And when he sat in it, the water overflowed, and it hit him, and he yelled, "Eureka! I've discovered it!" And he ran down the street to his house with no clothes on, and at least that's the story. So the idea is that he discovered, because he displaced water, he discovered that the buoyant force, the lifting force, is equal to the weight of the water that you displace. And if you don't displace, like if you're not underwater all the way, it's just equal to the weight of the water you displace with the partial buoyancy or partial submerged body. Some important terms here: submerged weight equals the weight original in air minus the weight loss. and you're going to need to be able to calculate the submerged weight. The specific gravity is equal to the weight in air over the weight loss when submerged. So that's what he did. He calculated the specific gravity of gold of the crown. And remember that specific gravity is basically equal to the density, but it has no units. Specific gravity is the proportion or the ratio of the density of the object to the density of water. Since density of water is 1, you basically just see the units go away. So it's the density without units. So here's just a visual of this Archimedes crown, and you can see that you've got the submerged weight, and this is what he actually did. I think he used a balance with weights, but he actually weighed the crown underwater, and he weighed it in dry air, and remembering that the weight is equal to mass times 9.81 meters per second squared. You can see that there's a difference here. So you've got the dry weight of 14.7, the submerged weight of 13.4, and the difference of that you could subtract and use that to determine the specific gravity like we just did. I also have some examples of practice problems to do for this, and be very important, I think, just to do 2 or 3 of each type of problem in this chapter, including the crown problem. So work through those examples that I've got with solutions and make sure that you can get through that. So we'll finish up talking about calculating buoyancy, and the whole idea in buoyancy when you start with these problems is to set the force of buoyancy equal to the force of weight. In other words, the amount of lift is equal to the amount of weight because you're in equilibrium. When you're in equilibrium, you're not moving, or you're in some cases you could say you're in equilibrium when you're going at a constant velocity and not accelerating. Here, we're not moving when you're floating. So FB equals to force of weight. The next step is to say density of the object times the volume submerged times 9.81. So that would be the force buoyant, because the density times the volume times 9.81 is equal to the force. And then we look on the other side, and we also have DVG, density of the water displaced times the volume submerged times 9.81. So you start with this, and I've got 2 or 3 of these. I would work through one that has a balloon in the atmosphere. I've got a solution that you can work all the way through with that in the example problems. I would work with one that's like a raft that's partially submerged and try to calculate how much the raft could hold before it goes under. But all of them start out with force buoyant equal to force weight, and then the very next step on that is your DVG equals DVG. And if you'll start with that step, the problems kind of just I won't say solve themselves, but it'll be a lot easier for you to do those. Make sure that you do at least one example that has the balloon, one that has a raft, or something floating in a fluid, and there are a couple other varieties of that. So that finishes up what we're going to do on this first section. Work through those examples and then get back to me. Good luck.